All right, today we're going to deconstruct LEO, a really landmark paper that basically gave AI agents a body. For years, these incredibly powerful models have been stuck in the 2D world of text and images. What this research did was give them the ability to actually perceive, reason, and act in a 3D space. So let's break down exactly how they pulled it off.
Just think about the AI you interact with every single day. They are brilliant at language, they're fantastic at reasoning, but they are fundamentally disembodied. They're like minds without bodies, trapped right there behind our screens. They can't really, truly interact with our physical world. And this limitation, this is the exact problem that the LEO paper set out to solve.
So before this work, you could say that most powerful AI lived in a kind of flatland. Their intelligence was all abstract, built on text and 2D images. The goal here was to create an embodied AI, one that doesn't just process the idea of a chair from a picture, but can actually ground that concept in the physical 3D data of a real chair in a real room.
And the authors, they identified this as a fundamental bottleneck. Think about it. True general intelligence requires interacting with the world we all live in. If an agent can't understand 3D space, its ability to perform useful real-world tasks is always going to have a ceiling. It's the difference between describing how to make coffee and actually being able to make it.
So, to escape this flatland, the researchers introduced a pretty groundbreaking new agent architecture, and they called it LEO.
The author's own words here really capture the sheer ambition of the project: perceive, ground, reason, plan, and act. Now, this is the key insight for any developers out there. LEO isn't just a vision model that's been bolted onto an LLM. No, it was designed from the ground up as one single, unified system for embodied interaction.
The really crucial point here is that LEO is a generalist, not just a patchwork of different models stitched together. It takes in everything all at once: 2D camera views, 3D environmental scans, and text commands, and its brain, which is a single language model, decides the output. And that output can be language, it could be a physical action, or it could be both. Okay, so that's the what, but how did they actually build this thing? Let's take a look under the hood at the architecture that allows an agent to see and act in a 3D world.
The architecture is surprisingly elegant. All these different inputs, the 2D camera view, the 3D data, the text commands, they're all converted into a single stream of tokens. This one unified sequence gets fed into a large language model, which then generates a unified output. That might be a text response or an action token like move forward. By using a capable open-source model like Vicuna 7B and fine-tuning it efficiently with LoRa, they essentially turned a standard LLM into the brain of an embodied agent.
Now, this whole thing required a really clever two-stage training process. You can't teach an agent to act before it can see, right? So in stage 1, the vision-language alignment, they first taught the model to connect 3D objects with their text descriptions. It was only after it learned to see and describe the world that they moved on to stage 2, vision-language action tuning. And that's where they taught it how to follow instructions and perform physical tasks.
Of course, an agent like this is only as good as its training data. And a huge contribution of this paper was how they created it. They built 2 massive new datasets, but the real innovation was their LLM-assisted pipeline. To generate high-quality 3D descriptions, they used a technique called object-centric chain of thought. Basically, this means they prompted an LLM to first identify all the objects in a scene, describe their properties and how they relate to each other, and then write the final summary. This step-by-step reasoning dramatically improved the data quality, which is a critical lesson for anyone building agentic systems. Your data generation pipeline is absolutely paramount.
So after all that incredible architectural innovation and data engineering, what can LEO actually do? Does it live up to the promise of being a true generalist? Let's take a look.
First up, 3D captioning. LEO doesn't just see a door. It describes its precise location relative to the room, in the middle of the northern wall. This shows a really sophisticated level of spatial grounding, which is a key part of its perception.
Okay, so from perception, we move to action. Given a command like put the blue blocks in a green bowl, LEO has to parse that sentence, identify all the blue blocks, find the single green bowl, understand the spatial relationship of in, and then generate the exact motor commands to get the job done. This is where embodiment gets real.
LEO can also navigate its environment, so when it's tasked with finding a counter, it has to chart a course through a cluttered 3D space, constantly updating its internal map based on what it's seeing. This is a core skill for any autonomous agent for sure.
But perhaps most impressively, LEO can handle abstract, high-level commands.
When a human just says, organize and tidy up the bedroom, Leo leverages the reasoning power of its base LLM to break down that complex goal into a logical series of smaller, concrete actions. This ability to plan is really what separates a simple bot from a truly intelligent agent.
Leo was a huge achievement, no doubt, but like all great research, it also illuminated the path forward by revealing its own limitations and opening up a whole new set of questions.
And to their credit, the authors were really transparent about LEO's limitations. For one, it struggled to generalize to completely new, unseen environments. They also highlighted what they call a critical vision-language-to-action gap. In other words, there's a big difference between knowing a cup is on the table and having the fine motor control to pick it up without knocking it over. And closing that gap is crucial for real-world robotics.
These limitations point directly to the next wave of research. The field needs to create larger, more diverse 3D datasets to improve generalization. We need new breakthroughs to bridge that gap between perception and action. And of course, as these agents get more capable and more autonomous, the work on safety and alignment becomes absolutely non-negotiable.
And that brings us to the final, critical question that this paper really leaves us with. Leo's triumphs, they all took place inside a simulation. So bridging that gap from the clean, predictable world of a simulation to the messy, chaotic, and infinitely complex physical world, well, that's the next great challenge for agentic AI.
This is for entertainment purposes only.